Hello everyone, my name is Gennady Gor and I'm gonna talk today about compressibility of supercritical methane in nanopores, a molecular simulation study. First of all, I want to mention the authors of these work, Nick Corrente, who was an undergraduate student in my group, and Chris Dobrzhansky, who was a PhD student in my group till recently when he defended his thesis in April. And also I want to mention that this work was published in Energy and Fuels earlier this year, so you can get all the details if you'd like in this article. All right, motivation for this work. So we're studying confined methane. Why confined methane? Well, it's hopefully pretty obvious. All unconventional hydrocarbons have to deal with confinement, right? And unconventional hydrocarbons include coalbed methane, shale gas, shale oil, and the difference with conventional hydrocarbons is that these systems are nanoporous, and so the hydrocarbons are confined to nanopores and typically present in the adsorbed state. And to illustrate that, I'm showing a couple of SEM images for shales showing the porosity in the nanometer range. Well, that's the motivation for studying confined methane. Now, why compressibility? In geophysics, wave propagation in porous media plays an important role. It's used for characterization of formations and it's used for characterization of samples. And the wave propagation of porous media is determined by various elastic moduli. And if we're dealing with the fluid saturated porous sample, we would need to take into account the moduli of the solid, Ks, the modulus of the porous solid, K0, and also the modulus of the fluid in the porous, which is denoted as Kf here. Furthermore, there are equations which relate the overall modulus of the composite to the modulus of the constituents, and as you see, the Kf is here in these equations. So we would like to know what this modulus is in order to describe the wave propagation in porous media, if these porous media is geological formation with methane, right? So there has been some earlier results looking at the elastic properties of fluids in confinement. In particular, a few years ago, a work by a German group reported the measurements of elastic properties of argon confined in the pores of Vickers glass, and these data is shown as the colored markers here on these plot. Well, in particular, what they showed that the modulus of argon in confinement differs from the modulus of argon at the same conditions in bulk. Well, furthermore, we showed that from molecular modeling combined with the Gassman equation, the equation for the properties, elastic properties of the composite, we can predict the modulus of the fluid saturated Vickers sample quite close to experimental data. So these two lines are the results of our calculations while using two sets of slightly different parameters. Furthermore, the simulation showed another interesting trend, and these data is the data for nitrogen adsorbed in silica pores of different pore sizes. And as you can see here, the modulus of liquid nitrogen in the pores exceeds that dotted line, which is the modulus of bulk liquid nitrogen, while the moduli here, the crosses here represent the moduli in the pores of different sizes. And furthermore, the dependence on the pore size is very simple. It's a linear dependence of over 1 over pore diameter. So while we studied these for subcritical fluids, argon and nitrogen, and we showed that the confinement changes the modulus, the elastic modulus of the fluid. And the question is, what about supercritical fluids? And this is what this work is focused on. Methane at supercritical conditions in the pores and what the elastic properties would be. All right, I'll start from reminding a couple of definitions. So typically in thermodynamics, when we talk about elasticity or compressibility, it's convenient to consider isothermal compressibility, these derivative, where V is volume, P is pressure, N is number of particles, and T is temperature, or reciprocal property, which is more convenient when we consider wave propagation in porous medium, the isothermal bulk modulus, which is 1 over compressibility. If we consider a system in the grand canonical ensemble, so that with fixed chemical potential, but the system is able to exchange particles with external reservoir, the compressibility or the bulk modulus can be expressed with this simple equation, where basically the modulus is calculated from the fluctuation of number of particles in the system. Well, strictly speaking, this equation is written for the bulk system. However, it has been applied for the system, for the fluids in confinement, and showed to work well. Therefore, we're going to be using this for our calculation. Well, in addition to simulate the system in the grand canonical ensemble, we would like to simulate it in the canonical ensemble. And in fact, there is a way to express the modulus of the system in the canonical ensemble as well. So it is given by this expression, where W is the virial, X is the hypervirial, and basically the elastic modulus is determined by fluctuations of the virial in the system. So the virial is obtained from the forces. For the forces, the forces are obtained from the derivative of the pair potential. And what's important here, that unlike the grand canonical ensemble, which can be used only with Monte Carlo simulation, the canonical ensemble can be also used with molecular dynamics simulations, which is, well, more universal tool. And of course, molecular dynamics simulations for fluids in the pores is quite straightforward. So thus here we will be showing the results not only from GCMC but also from molecular dynamics. We will consider the following system. We'll consider methane in carbon slit pores with the pore sizes, where the pore widths varying in the range from 2 nanometers to 9 nanometers, which is this range is called mesopores. We consider 2 different models for methane. We'll consider the Lennard-Jones methane and trap explicit hydrogen methane, because in fact, while the derivative properties such as compressibility, they're quite sensitive to the details of the force field, to the details of the representation, so more sensitive than the number of particles or pressure and so on. So the temperature range is 298 to 332 Kelvin. The pressure is between 1 MPa and 10 MPa. And we run the GCMC, Grand Canonical Monte Carlo simulations, using the RASPA code and molecular dynamics in LAMPS. And I want to say that this system with these parameters we chose following the paper by Mosher and co-authors, where they simulated adsorption isotherm in the context of enhanced coalbed methane recovery. So we decided to exactly replicate their systems, well, except for we calculate compressibility rather than just adsorption isotherms. All right, we started from a simple consistency check, reproduced the adsorption isotherms, and also predicted the modulus of bulk methane before calculating it in confinement. So the adsorption isotherms using, well, both united atom and explicit hydrogen methane, well, meshed nicely with the isotherms from the Mosher paper. And also when we calculated the elastic modulus using different models, they all were consistent for the bulk methane, and they were also consistent with the elastic modulus predicted based on Peng-Robinson equation of state. So these are the results for the confined system. So here we show the isothermal modulus as a function of methane pressure in the pores. Well, the line shows here, the line is the modulus of bulk methane at these pressures, and while this is all at constant temperature of 298 Kelvin, the red markers correspond to 9 nanometer pore, and the blue markers correspond to the 2 nanometer pore using different models. So what we see here, first, well, the modulus of confined methane always exceeds the modulus of bulk methane. Second, the smaller the pore size is, the larger is this deviation between the modulus of the confined methane and the modulus of the bulk. And also we see a monotonic trend. We see that the modulus increases, well, be it confined methane or bulk methane, it increases monotonically with the increase of pressure. Well, it's also interesting to look at the modulus as a function of pore size. So here, each curve corresponds to a certain pressure value. So this line is 1 MPa, this line is 4 MPa, and this line is 10 MPa. And the modulus is represented here, it's all at constant temperature, as a function of the reciprocal pore size, so 1 over the pore width. And as we can see, so the smaller the pore is, the greater would be the modulus. Furthermore, these increase while at low pressure. It's actually pressure below critical pressure. This trend is pretty much linear. While when we go to higher pressure of 10 MPa, the trend is faster than linear. While also what is worth mentioning, the agreement between GCMC and MD and also united atom and explicit hydrogen models is pretty good as well. All right, why is that happening? Why do we see it? Because when we consider methane in the pore, the density in the pore won't be uniform. If the pore is large in the center, the density will be close to bulk. However, by the pore walls, the density will be higher, and these dense layers will give us higher modulus. So for smaller pores, the contribution of this layer obviously increases, and the modulus overall increases. All right, one more thing which I want to mention before concluding is the dependence of the modulus on the pressure. Well, for every pore size, we can see these linear trends. This is actually a well-known equation, an equation known as Tate-Murnaghan equation, which goes back to 19th century. So the modulus, the elastic modulus, is linear as a function of pressure within a wide range of pressures. Well, the difference between what we've known before and what we see here is that for subcritical fluid, we saw that these slopes were the same for all pore sizes. Here, we see that for different pore sizes, the slopes are different. All right, with that, I'd like to conclude. So first of all, wave propagation in porous media is determined by elastic moduli of solid and fluid constituents. Thus, the elasticity of fluids in nanopores is important. Well, we calculated the elastic modulus of supercritical methane confined in carbon pores using molecular simulation, Monte Carlo NMD. Our simulation showed that the elastic modulus of confined methane is higher than in bulk. For a given pore size, the modulus monotonically increases with pressure. At a given pressure, the modulus monotonically increases with the reciprocal pore size. And finally, these effects appeared much more pronounced than for subcritical fluids, showing up to 7-fold increase of the modulus in 2 nanometer pores. Thank you for your attention.